Hello, I'm Michael O'Connell, and in this video we are going to derive the lever rule, and we're going to use it to explain how the ratio of vapor-liquid fractions changes in a closed container of a binary mixture at a fixed temperature as the pressure is increased and the contents transition from all vapor to all liquid. So, I snipped the plot that we created in a previous video, in which we have the bubble pressure curve and the dew pressure curve changing with respect to the mole fraction of the more volatile component. And what I want to talk about here is this yellow dot, and that is the mole fraction of the more volatile component in our feed that is coming into this closed container, we could say. And basically, because we are at this pressure at the 393 kelvins, that constant temperature, we are in between the bubble pressure and the dew pressure curve. So obviously, with the more volatile component here, we are going to have a mole fraction of that material in the liquid phase and a mole fraction of that material in the vapor phase as well. And those are represented by the blue and red dots there. Okay. Now, obviously, remember, this is done at constant temperature, and we have the pressures here on the y-axis. So when we're at higher pressures for this binary mixture, right, that's above the bubble pressure curve, then our binary mixture is completely liquid. Likewise, if we are below the dew pressure curve at low pressures, our binary mixture will be all vapor. So we are going to look at this transition. So let's derive the lever rule and see how that will actually help us. And we can start this by doing a mass balance, right? Because we know that the total material here that is coming in at some moles per second is going to be equal to the flow rate of moles per second, right? The vapor that's exiting from the top and the liquid that's exiting from the bottom if we're talking about a flash drum, right? Which we talked about in one of the previous videos. But we can do the mole balance or the mass balance by multiplying each of those terms by the mole fraction, right? Where Z is the mole fraction of that component in the feed, then Y is the mole fraction in the vapor phase, and X is the mole fraction in the liquid phase, of course. What we can do now, because we're trying to get this vapor/liquid ratio, we want something with V over L, right? Because that would be unitless, which is a true ratio, right? And because we want V over L, we can perform this substitution, right? Where we know that the feed rate in moles per second is equal to the flow rate in moles per second of vapor that's exiting from the top, plus the flow rate in moles per second of the liquid phase material exiting from the bottom. So we do that, and then what we can also do is distribute this term, right? The mole fraction of said material in our feed. And what do we want to do here? Well, what we're going to want to do is move, let's see. We want to move stuff around a little bit, don't we? Because what I would desire here is to have probably the terms with L on the left-hand side, let's say, and the terms with V on the right-hand side, right? Because what will that allow us to do? Well, basically, like I said, we want to have this ratio of vapor and liquid fractions, correct? And this will allow us to do just that, won't it? Because as you can see here, we can factor out V from the right-hand side, and we can factor out L from the left-hand side. So let's see what that gives us. Now, obviously from here we can do some division to create a fraction that would represent the ratio of the material in the vapor phase over the material in the liquid phase, right? So V over L. So I divided both sides by L, and then I can divide both sides by this term, the mole fraction in the vapor phase subtracted from the mole fraction in the feed. So let's see what that looks like. Because this is what we're talking about when we talk about the lever rule. What we need to think about here back to our plot is what actually is being described by this z minus x and the y minus z. The lever rule is basically saying that the ratio of vapor to liquid phase that we would obtain for our binary mixture here is equivalent to the ratio of these two distances, white over green in this case. Now, why do I say white over green instead of green over white? Well, let's use our equation that we derived to justify what I have said. We have z minus x, which is the mole fraction of said component in the feed, subtracted from the mole fraction of that component in the liquid phase here in blue. So that's the white. That's what that distance would be, correct? When we do the difference. The distance in green there is the mole fraction in the vapor phase of that component subtracted from the mole fraction in the feed. So that's what this describes. So now you kind of understand what the lever rule is all about. And what we can look at now is what will happen when we increase the pressure. So as we increase the pressure, this yellow dot moves up and up and up. And as you can see exactly what would happen, right? See how this white line I have drawn starts passing through the bubble pressure curve, which means in reality it would be getting shorter. But this green line is going to get longer. So basically, again, we're increasing the pressure. So we know we're going to get more liquid phase. And that makes sense, right? Because again, look at these denominators. We have the amount of liquid phase, right, over here. And then this distance, y minus z, the mole fraction in the vapor phase minus the mole fraction in the feed for us, for this binary mixture. So this makes perfect sense, right? And basically, when you get to the blue curve, the bubble pressure curve, this time we're going up, right? We're not going down. So this isn't actually the way we would find the bubble point necessarily, in which we're trying to see when the first bubble of vapor forms. In this case, right here on the bubble pressure curve, this would be when your last vapor bubble condenses into liquid, right? Because you're at that pressure where now if you go past the bubble pressure curve, now our binary mixture is completely composed of liquid. And obviously we can go the other way too, right? At the same way. We can decrease the pressure and keep decreasing it. And then again, when we would be right here, you would have that last little bit of liquid evaporate into the vapor phase. And likewise, you would see this white rectangle I have representing the distance that is given by this numerator, z minus x. You would see that increase as we decrease the pressure. And of course you would see it increase because, again, what the lever rule is describing is that is effectively representing through this relationship, these ratios. That's also indicative of the fact that the amount of material in your vapor phase is increasing as you decrease the pressure, of course, isothermally. So hopefully with this explanation, you can kind of understand why this is called the lever rule. Because if you think about these two lines, the green and the white, kind of like a lever, right? Or a lever. Like a teeter-totter, right? So as I increase the pressure, right? As we increase the pressure, the vapor phase starts to increase and the liquid phase starts to decrease. As I decrease the pressure, the liquid phase starts to decrease and the vapor phase starts to increase. Okay? So you can really think of it just like a teeter-totter when you're at the playground. So with that kind of weird and funny explanation, at least I might be the only person that thinks it's a little bit funny, I will end this video, and I hope through all these 5 videos you learned a lot about vapor-liquid equilibrium, especially with binary mixtures. But again, we can use this for mixtures that have a ton of different components as well. We just went with the most simple case. But hopefully All of this gives you a very, very good understanding about vapor-liquid equilibrium, and specifically with this video, an explanation on the lever rule, how we can explain how the vapor-liquid fractions, the amounts, are going to change as we adjust the pressure at a fixed temperature. So thank you so much for watching.